Well, the purpose of this screencast is to take some notes on forces and Newton's three laws of motion. We'll look at some examples of how to draw force diagrams and different kinds of forces acting on objects. So to start out with, you'll want to write down some things about what is a force. So typically, especially at the elementary grades, a force is defined as a push or pull on an object. And something about forces is that the direction does matter. So we'll be looking at if it's to the right, to the left, up, down, things like that, where it's exerted on the object will matter. And the unit of force is a Newton, or a kilogram meter per second squared. So we've already discussed this a little bit in class, but Newton's first law of motion is stated as an object in motion tends to stay in motion, an object at rest stays at rest unless it's acted on by an outside force. And another term you may have heard is called inertia. That's the property of an object to resist a change in motion. So typically things that have a lot of mass will have a lot of inertia. It's harder to change their motion. And we'll play with some bowling balls and croquet mallets in class to see this in action too. So some examples of Newton's first law would be, if you're in a low friction environment, maybe you're on roller skates or on ice skates, if you push off against the wall on a really smooth surface, you'd keep moving, you'd stay in motion because there wouldn't be a lot of other outside forces acting on you. Eventually friction might act to slow you down, but if you're in a really low friction environment, you'll keep moving for quite a while. Also in outer space, if you've ever seen somebody, give a force to something and release something or push something, it just keeps going and going. There's nothing to change its motion. All right, so Newton's second law is typically stated as F equals ma, but the formal statement then would be that the acceleration of an object is related to the net force or total force acting on it. Is in that same direction, and it's inversely proportional to the mass. So if we take a look at this equation, acceleration here's related to force and mass. So if you exert a force on a smaller mass, that means that the smaller mass is going to give it a larger value for the acceleration. So that's what's indicated here. You push on a small object, it's going to have a big change in its motion or a bigger acceleration. If you exert that same force on a larger mass, maybe a large rock or something like that, it's only going to have a very small acceleration. So when this denominator is bigger, the acceleration or change in motion of that object is going to be smaller. So that's an example of Newton's second law. And Newton's third law is typically stated that for every action there's an equal and opposite reaction, and we'll typically talk about this in terms of forces. You always have to have a force that's an interaction between two objects. And these pictures show a couple of examples. If a tire is pushing on a road, the road pushes on the tire. So the words that you're using for these forces, these objects involved in the forces, always have to be the same. Tire, road, road, tire. If a rocket pushes on some gas particles, the gas particles push on the rocket, and the size of those arrows is the same. A man pulls on a spring, the spring pulls back on the man. And the one that I think is a little bit trickier is that if the earth is pulling down on something, like the force of gravity on an object, the reaction force is then that the ball has to pull on the earth. But the earth is so massive it doesn't really notice it that much. Alright, so the way that we're going to represent forces, as you already saw, is by using arrows. And so the size of the arrow indicates the strength of the force acting on something. So in these pictures, you can see that the first block has two forces acting on it, one towards the left and one towards the right. You can think about almost a tug of war, something people pulling on it from each side, but they're equal to each other, 3 newtons in each direction. So on this one, though, we can see we have 3 newtons pulling on it to the right and 5 newtons pulling on it to the left. So if we wanted to know what the net force is, we're going to have to define the to the right as positive and to the left forces as negative and add them up. So on this one, if we had -3 to the left and 3 to the right, it would add up to 0 newtons, so a net force of 0 newtons. The one on the right We have 5 to the left and 3 to the right, so that gives us a net force of -2 newtons, or 2 newtons to the left. And so if we wanted to draw a picture of the force, the net force on that block, it has to be whatever the size of this one is, subtracting out the size of that one, and whatever's left over would be about 2 newtons there. Now, if we suppose that we know the mass of that second block, what would be its acceleration, and how could we describe the motion? So we already found the net force to be -2 newtons, so then we can use that equation for acceleration is equal to net force divided by mass, and figure out that -2 newtons divided by the mass of 1 kilogram, so it would give us an acceleration of -2 meters per second squared, or -2 meters per second. And that means that the negative sign means that the acceleration is to the left in the negative direction, and the acceleration is 2 meters per second squared. So it's going to be increasing its speed to the left. So if there's this net force acting on the block here, it's going to speed up to the left. So this brings up an important point about the difference between unbalanced versus balanced forces. So an unbalanced or net force is always going to result in some kind of change in motion. Either the object is going to speed up, slow down, or change its direction of its motion. In this case, if the object is starting from rest, it's not moving initially, it's going to speed up to the left on this one here. But if the object were initially moving, let's say it were initially moving to the right, and then there's a net unbalanced force acting to the left, what would happen is it would start to slow down. Eventually it would come to a stop, and then it would start moving in the opposite direction with increasing speed. And you've probably seen this before too. If you throw a ball up in the air, you know that the force of gravity is acting down on that object, and so as you throw it up, its motion is in the opposite direction of the net force, and so it starts to slow down. Eventually it reaches the top of its path, comes to a stop, and then it turns around, and then after it turns around, the force of gravity is acting in the same direction as it's moving, and so it starts to speed up in that direction. A balanced force can result in two situations: either no motion, the object just stays at rest, or if it's already in motion, you could have constant velocity motion. So in order to have something speeding up or slowing down, you would have to have an unbalanced force. So there's some examples of different kinds of forces, and these are in the lecture notes as well. One example that we've talked about in class before is the force of gravity, or weight. So that's the force of the earth pulling down on an object, and we typically draw that as an arrow coming from the center of the object and directed downwards. And we label it with an F and a small g to mean the force of gravity. The normal force is something that has to do with the contact on a surface. Typically, if something's on the ground or on a table, we draw the normal force as acting perpendicular to the surface. So if this is the surface, it's at a 90-degree angle to the surface. If something's on an incline, you have to have it at a 90-degree angle to that incline. You can either draw the normal force acting at that surface location, or at this directed from the center of the object. Friction is typically, when things are in contact with each other, rubbing on each other, it's always going to be acting to oppose the direction of motion. So if the object is moving this way, friction is going to act in this way to try and oppose that motion or resist that motion. So you can either draw a friction force acting at the center along the surface that the object is at, or pushing on it directed at that surface location as well. And the last kind of force we're going to talk about is tension, and that's typically when there's a string or something attached to the object. We'll say that there's a tension force on it directed along the direction of that string away from the object. And you can have other kinds of forces that are like pushes and pulls to applied forces. So let's practice drawing a couple different force diagrams. So one situation is, suppose you have a coin that is falling down a wishing well. So in this situation, we're going to assume that the air friction exerted on it is really small. So we're just going to ignore the force of air If we didn't ignore it, there would just be a small amount of force that we would draw on it. So in this case, though, the only force acting on the coin then is, after it leaves your hand, is the force of gravity, or the force of the earth pulling down on it. So we draw a picture of a coin, and then we would draw the force of gravity pushing down on it, or pulling down on it. That would be an unbalanced force, so the object would start to accelerate or speed up as it gets further and further down the wishing well. So another situation would be, suppose a book is sliding horizontally to the right along a surface of a rough table. So maybe you gave it a push and then you let it go, and it starts sliding to the right along the surface of the rough table. And so we're going to assume before it comes to a stop that there's some friction acting on it, since it says it's a rough table. So after it leaves your hand, there's no longer an applied force or a force from your push. So we can look at both the vertical and the horizontal forces acting on this book. We'd have gravity acting down. Then the normal force you can either draw on the surface or directed from the center of the object, and it's perpendicular to the surface. And then we're going to say, since the book is moving horizontally to the right, in the direction of the right, the friction force has to be directed opposing that motion, or to the left. And so if it's initially moving to the right, there's an unbalanced force in this direction opposite to the direction of motion, so it would cause the book to slow down and eventually come to a stop. Alright, so the last one is if you push on a shopping cart in a straight line at a constant speed. The key word here to take notice of is constant speed. Remember that constant speed means that it can be produced by balanced forces. If you have unbalanced forces, it'll always result in acceleration. The object will be speeding up or slowing down. So in this case, that means that the force that you're pushing at has to be equal to the force of friction acting back on it. So if we were to draw a picture of this, we could identify the vertical forces, like the force of gravity pulling down on it, and there's a couple different ways you can draw the normal force, either directed at the surface, like by the wheels, or from the center of the object. So this is what it would look like if it were from the wheels. I split it up into two normal forces, but when you add them up, it's still the same size as the force of gravity pulling down, because there's no acceleration happening in the vertical direction, so they have to be balanced. And then if you show yourself pushing on this cart, that has to be exactly balanced by the force of friction acting on the wheels. So another way you could draw that normal force would just to be directed at the center of the object, and you can see the size of the arrows is equal here, and the size of the arrows is equal here, so we have constant motion. Alright, so in your workbook there are several other questions about force and motion that we'll explore in class, and then on your own time you can also look at some of the additional practice questions that are in the workbook at the end of the review guide.